Hello, my name is Walter Alexander Nahra, and I'm a student at California State University in Los Angeles, and these are my notes for week 8 of CS 4540. The advancements of AI in recent years have largely focused around scaling up models through increased data and computational power, without changing any of their architectures like transformers. The costs required to train these models have surged, prompting discussions about the sustainability of continued scaling. Given the amount of money that are put into these AI chatbots, you would assume that these are some of the most sophisticated models ever seen. That in most cases, that they're capable of answering even the simplest problems. Now, let's put that to a test. We'll give the AI chatbot a problem to solve. The scenario is what follows. Oliver picks 44 kiwis on Friday. Then he picks 58 kiwis on Saturday. On Sunday, he picks double the number he picked on Friday, and then five of those kiwis are smaller than the rest. When it comes to human results, combining 44 kiwis on Friday plus the 58 kiwis on Saturday, and then multiplying the 44 kiwis by two to get us the total amount of kiwis that Oliver picked on Sunday, which is 88, we come up with the result of 190. However, if you were to give this problem to the AI chatbot, it'll come up with the number 185. So taking the total amount that we took. So why is that the case? Well, it comes down to the little detail. While the sizes of the kiwis doesn't affect the overall total of kiwis, the AI model believes that this extraneous detail, that five of the kiwis are smaller, is important and thus hallucinates a bad answer to the problem. This is what we refer to as probabilistic pattern matching. The LLMs, which are the backbone of AI chatbots, are searching through their trained data for the closest data that matches the given data or user's prompt. In this case, the closest data had examples where these caveats are taken into consideration. This is due to these examples having a purpose reason to include these details. As such, the program bases their reasoning on these examples, thus influencing the results regardless of their application. And this is where the concept of token bias comes into play. LLMs are effectively predicting the next token in a sequence, and the reasoning output of the model changes when a single token of input changes. The tiniest little tweaks in how an individual phrases their question to these models have an outsized effect on the reasoning presented in the output. Thus, a chatbot that appears to be reasoning may just be doing a super sophisticated autocomplete where it's guessing the next element without having a proper understanding of the underlying concepts, which can often lead to scenarios of hallucinations when the prompt structure confuses the system. Now, this brings up an interesting question. Are AI models capable of thinking? Our understanding of that are attributed to individuals who not only express a sense of understanding and adaptability centering around goals, but also a sense of consciousness. AI models, especially AI chatbots, create the appearance of thinking without having actual awareness, no comprehension of what they're producing. So to answer the question, AI models don't technically have the capabilities of thinking for themselves. However, while true thinking is not achievable at their current state, we could still implement techniques and tools that could push these models to take more into consideration their actions and what they output. Some of these techniques for AI thinking include training time compute. This refers to the computational resources like processing power and memory used during the training phase of a machine learning model. An example of TTC is train of thought prompting. It's an AI technique that helps models break down complex tasks into a series of logical steps, improving models' reasoning and accuracy. For example, prompting models to utilize step by step into their reasoning steps before producing an answer, thus allowing the models to think about their response before pushing them out. And then we have inference time compute, or ITC. It refers to the computational resources and time required for a trained machine learning model to make predictions or generate outputs on new unseen data. For example, prompting the models to spend some time thinking before giving an answer with the amount of time spent on thinking is variable based on how much reasoning the model needs to do. What that means is that short tasks would take roughly a few seconds, while longer tasks may take roughly a few minutes. The inference reasoning is something that can be tuned and improved without having to train and tweak the underlying model. And then this brings up the concept of system one and system two. System one thinking refers to quick instinctive responses. This is actually what many AI models were built upon, utilizing System 1 capabilities in order to execute immediate decision/responses. System 2 thinking, on the other hand, refers to a more deliberate and analytical approach to responses. Understanding the benefits of System 2 capabilities will allow for more superior outcomes with the downside of more time taken for computation. Allowing a bot to think for even a small amount of time yielded performance improvements equivalent to scaling the model size and training duration vastly. Now, let's bring us a few examples of how giving the AI models more time to think before acting on their responses actually helps improve them. So let's take the game poker, for example. In the context of poker, it was observed that providing the AI with even short periods of think significantly improve its decision-making capabilities. Initial attempts pairing the AI poker bot against four top human players had the poker bot lost decisively, demonstrating the limits of immediate decision-making. Through reevaluation of their approach, the developers redesigned the bot to incorporate more thinking time. Subsequent attempts with the same scenario as the initial case had the poker bot triumph in most cases, highlighting the effectiveness of strategic thought processes over sheer speed. For our next example, we'll be looking at reverse tic-tac-toe. But before we discuss that, let's first introduce what DeepSeek is. Well, DeepSeek is a Chinese AI company started by Lang Wenfen in 2023, specializing in open source LLMs such as their DeepSeek R1 and DeepSeek V3, gaining traction for its cost-effective approach to AI development. DeepSeek R1 is a first-generational reasoning model developed by DeepSeek based on reinforcement learning, or RL, designed for logical and reasoning tasks, with capabilities on par with OpenAI's O1 model. Let's also bring up what reverse tic-tac-toe is. The rules of reverse tic-tac-toe is somewhat similar to a regular game of tic-tac-toe. The objective of the game is to force the opponents to complete a line of three X's or O's, either horizontally, vertically, or diagonally. It's played on a 3x3 grid. The game is a draw if neither player complete a line of three after the grid is filled. Strategies of reverse tic-tac-toe often employ players to avoid creating a line of three while trying to force your opponent to do so. Blocking your opponent and creating situations where they are forced to complete a line is key to winning the game. The certain square is still a powerful position, but the corners and edges also play a significant role in creating multiple threats. In the first round of reverse tic-tac-toe, where the computers are represented by O's and the players are X's, the player's first move is to place an X in the sixth position, so the middle row all the way to the right. Then the computer places their O's into position 5, which is right in the middle. The player next chooses position 8, which is the one directly beneath the fifth position in the third row. Then the computer chooses position 1, which is right here. And then the player chooses position 7, which is down here. And then finally, the computer places its 0 on position 9, thus creating a diagonal, meaning that it loses the game. Now, the computer, despite losing the game, continues asking the player to decide their next move, resulting in the player having to inform the computer that they lost. The computer unknowingly lost their game by not thinking ahead of what their decision would mean in the long term and not considering the current state of the board/grid. This highlights how human intuition and oversight can still outperform AI in certain scenarios. Now, the result of this game it was based off of utilizing DeepSeek AI at its basic form, but for the second round, the player decides to change the AI model used by the chatbots to the DeepThink R1 version, which enhances the chatbot's reasoning and problem-solving abilities by allowing them to think more deeply about the task. So for the second round of reverse tic-tac-toe, what the computer will do, it will constantly update the board after every turn on either side so that it will retain all the information about what the player and itself did during each of their turns. The computer will comb through every available position and considers potential next player movement to determine the consequences that choosing that position might have on the computer's chances on winning. Once the computer recognizes the best position for them, they tell the player their move and wait for their next move after the player already made theirs. And this will constantly be repeating until either the computer wins or it loses. Once the computer determines that they lose, no matter what position they choose on the grid, they recognize their defeat and won't ask the player to make their move, even telling the user what position to make them lose. Now, as we can see when we compare the two rounds, in the first round, the computer was seemingly choosing their moves at random, not taking into consideration the board nor their previous moves, as if the board was blank every move. However, in the second round, with turning on the R1 feature, despite still losing at the end, it took its time to really plan out their moves, thus making their decision more human-like. When it comes to the future of AI thinking and its role in our society, the current AI models primarily function as chatbots or immediate response systems, but focusing on scaling thinking time could recast AI's role in sectors like healthcare or scientific research. The future of AI development appears promising with emerging paradigms that focus on enhancing thinking and processing capabilities, which potentially could lead to groundbreaking applications that can tackle complex issues. However, as AI progresses, the financial sustainability of longer thinking periods and decision making will need careful consideration, potentially justifying higher costs for more complex queries. Now it's time for the references. This week, we had two videos and one document. The first video from IBM Technology, the video brings up the concept of AI thinking, bringing up its limitations and methods that could enhance these models' thinking. The second video is a TED Talk with Noam Brown, which discusses AI's role in the present day and how allowing AIs to think before responding could actually help them. This is where the poker game example comes from. We got it from this video. And then in the document, we have R1 plays reverse tic-tac-toe. The document is basically the conversation with DeepSeek AI and the AI playing a game of reverse tic-tac-toe with the player. So this is where you'll get the more in detail responses from the AI. Basically, it explaining how each position will either make it win or lose in the long term. And this is where the reverse tic-tac-toe example comes from. And with that, that's the end of my video. Thank you for watching and have a good day.